Okay, so thank you. So I don't think I've ever given 2 talks in a row, especially on 2 completely different topics. So because the topics are different, feel free to live in maybe not in the middle of the okay, so right, I'll talk about. So the first talk is about cover time. Of random walks on graphs, and this is joint work with Jonathan Harman at UBC and Lucas Tessier . Okay, so what are we talking about? We've got some finite graph. And so we're going to be studying random walk on this graph. So continuous time, discrete time doesn't really matter. Let's say continuous time for simplicity, for concreteness. And so we'll be interested in the cover time. So what is the cover time? So the heating time of the point X will be the first time that the walk is at X, and the cover time is just the maximum of all this heating time. Okay, so it's the first time the walk has passed by every vertex of the graph. And the sort of questions I think we want to answer are things like, you know, how big is it? Is it concentrated? What are fluctuations of the cover time? And maybe sort of a related question, which is concerned with the structure of the uncovered set close to the cover time. So let's call U of t. So this is going to be the uncovered set. So the set of vertices which should be not covered by t. And we can ask ourselves, what is the structure of this cover set, of the uncovered set? So is it clustered? Is it, you know, approximately product or correlated? I'm going to be asking these questions. You could ask this at any time, but we'll be asking these questions at times t that are close to, say, the expectation of the cover time. Okay, and so the motivations for asking questions like that, I think it's a natural question, but there's so beyond the natural, the fact that it's something natural, I think there are connections to interesting things. So to all the topics in probability. So it's closely connected to study of the Gaussian free field, evil quantum gravity. This is not in 2 dimensions. This would be closely connected. I believe it's closely connected to evil quantum gravity. It's not known to be the case. Also, other things such as random interlacements, which were introduced by Snitman precisely to analyze things like the structure of the uncovered set, to answer questions raised in physics on the nature of this uncovered set. Yeah, and there's okay, so there are many other things. So maybe let's start with maybe kind of the most basic example one can think of. So let's look at a torus. Okay, so just an m by m by m box. I'll try to reserve the letter n for the volume of the graph. So m to the d will be the volume of the graph, the size of the graph. And so let me write this as a theorem. And we have so let's take so really d equals 1 is quite special and not very interesting. So let's take d greater or equal to 2. And then what is true is that the cover time is always concentrated. So if I divide the cover time by its expectation, this converges to 1 in probability. And we can say more precisely how big this is. Maybe it's good if I remind myself. So furthermore, if I look at the expected cover time, I can always write it as something like write it t heat times log n. So t heat is the maximum heating time. So this is the maximum over x and y of how long it takes you on average to heat y. And what is this, you might ask? Well, actually, the behavior depends on whether we're in 2 dimension or in 3 and higher dimension. And so this is the advantage of using the letter n for the volume to make a comparison easier. And this will be something like c times n times log n if the dimension is greater or equal to 3. And it would be c times m times log n squared if the dimension is 2. The constant c is explicit, it depends on the dimension. And this was, highly non-trivial. This was proved by Gumbel, Perez, Rosen, and Zeytouni. Important paper in 2004. Yeah, so we have a different behavior in 2 dimensions and higher dimensions, and that's maybe not so hard to believe because, of course, random walk is recurrent in 2. This recurrence leads to maybe clustering of points that you visit, and so you might expect that the asymptotics in 2 dimensions are different than in 3 dimensions and higher. In 3 dimensions, we have transients, and you might expect decorrelation, and yeah, so you might expect a different behavior. So that's for kind of the first order behavior of this cover time. So study of the fluctuation is kind of even more recent than that. So this was obtained by David Belius 10 years ago, 2013, and he proved that if the dimension is greater or equal to 3, then the cover time is approximately n times log n, constant here, n times log n plus a random variable where this random variable is a Gumbel distribution. Which means that the probability that this is less than S, this is exponential of minus e to the minus S. I think this is correct. I always have to check this when S tends to infinity. 1 here, e to the minus infinity is at 0, exponential. Yeah, that's good. I always have to. So that's that. So really in the sense that if I look at the cover time divided by n minus log n, divided by Cn minus log n, then this converges to this Gumbel distribution. And this result is not expected to be true in dimension 2. In fact, we will see that it cannot be true in dimension 2. But this is not known. So are there questions so far? Feel free to interrupt me. So maybe one thing that I've kind of alluded to is that this Gumbel distribution, it arises as a maximum of ID random variable, let's say exponentials. It's max. ID random variables, say exponential, but it doesn't matter really. And the fact that you get a Gumbel distribution as the maximum of independent random variable suggests that really this uncovered set, it has, it's highly decorrelated, right? So, or if you want these heating times of points, they are the cover time is the maximum of this heating time. So the fact that we get the same distribution here and there suggests that these heating times are kind of independent, and so that the uncovered set might be decorrelated. Yeah.
By decorrelated, should I interpret it as collection of clusters of random size, which are?
I don't mean it in a very precise way, but I'll give a precise statement in a second. So before I do that, let me give maybe another example that I think seems naive, but I think is already non-trivial. So let's take a box. This is a three-dimensional box, M by M, but the height is variable. So height is somewhere between 1 and M. So if you took it to be M, this would be like a three-dimensional box. If you took it to be 1, this would be a two-dimensional box. So anything in between is sort of some sort of interpolation between these 2- and 3-dimensional cases. And you can ask yourself, depending on age, am I going to see something like a 3-dimensional behavior or 2-dimensional behavior? What about the fluctuations? Do you expect it to be decorrelated or not? So somewhere in between is a transition. Anybody wants to guess where the transition is?
There is a recurrence transition.
Okay. Recurrence transients, log n. You wanted to say something?
I guess log n.
Log n. Log n. Why log n? Michael, you ventured log n. Why did you say log n?
It's your talk, so
But you must have had an idea in mind. It's not.
That's going to be a longer story.
Okay, so it turns out it's right. It's log n, and also Ron is in some sense right. It's got to do with recurrence and transience, obviously, but not completely, as you will see. Not completely. So. By the way, I mean, you might be surprised that something so basic as that, we just don't know the answer. Turns out it's not obvious to study even an example as simple as that. Okay, so let me state a theorem. Yeah, maybe also before, you know, I'm writing things like that, you might think I'm just talking about boxes. If you want to think about sort of more exotic graphs, I would always restrict myself to vertex-transitive graphs, but even then, you know, this is a product of something that is recurrent, a two-dimensional object with something that is also recurrent, which is a one-dimensional object. But you can think of taking the product of something that's very recurrent in one dimension, in one direction, and very transient in another direction. And then what do you get? It's not obvious, right? So here's the theorem. This will always be, I don't know if we've got very good notation. This is a collection of graphs that kind of tend to infinity, but I'll use gamma both for the collection and for the graph in that collection. I don't know how to say it. So collection of vertex-transitive graphs. The size, I'll call it n, and it tends to infinity. I will assume bounded degree. So the following are equivalent. So first thing is that we've got Gumbel fluctuations. So scaled by the heating time, which I've introduced before. Maximum time it takes you to hit any point on average. Minus log n, n is the size of the graph, converge to a Gumbel, if and only if so d here is the diameter of the graph. So if and only if d squared log n divided by n tends to 0. I find that a bit hard to read. N is much bigger than d squared times log n. Okay, so that's an if and only if characterization.
Just a basic question. So when you have a finite box, why is vertex transitive?
Oh, yeah, sorry, periodic boundary condition.
Oh, I see. Okay.
It's really, yeah.
So by transitive, do you include graphs like which would locally be like trees, like they're uniformly?
Yeah, they can absolutely be locally looking like a tree. Yeah.
So you have a sequence of transitive graphs, and they don't necessarily have any relation to each other.
Yes, that's right.
Only have this connection.
Yes.
In the result, there is no dependence on the bound of the degree, right?
Yeah, that's right. But you know, I'm assuming bounded degree. You could allow for unbounded degree.
It's fine, just
yeah,
the letter.
Yeah. So it's equivalent to some completely global geometric condition, which maybe is kind of surprising. Ron's intuition was that it had something to do with local recurrence and transience. So this, I have to say, this was our kind of what Ron said was initially what we believed. So there is, I mean, these graphs are finite, so it's not clear what we mean by recurrence or transience, but actually you can make some nice definitions, I think. There are some nice notions of what it means to be recurrent or transient. So let me just say a few words about that because I found that kind of interesting. So there's two things. One is something we can call weak uniform transients. So gamma is weakly uniformly transient. Let's say if the max over all points in the graph, let's count the amount of local time. You start from X and you ask how much time do you spend at Y before, let's say, the mixing time. And you would like this to be bounded uniformly. So let's agree to call a graph weakly transient. If before you mix, what is this mixing time? Already many of you know, this is the first time that the total variation distance between the low of the chain and T and the uniform distribution dropped below, let's say, 1/4. Doesn't really matter what you pick here. It's a mixing time.
Was also Y again?
Yeah, so number of visits to Y. So so here I'm in continuous time. So the integral x equals y ds. Total time spent at Y. It's called the local time. That's why it's got an L. So yeah, let's call the graph weakly transient if it doesn't spend on average much time before it gets lost into the graph. So before the mixing time, and so that's the weak transients. There's a strong notion of transients, which is that so this is slightly more demanding. So gamma tends to infinity, max all points. So let's count the local time spent at Y, but only between some fixed time T and the mixing time, n tend to infinity, then T tend to infinity, that should be 0. Okay, so after some fixed large time, you're not going to, after time 1,000,000, you're not going to spend any time at all, anywhere, at any fixed vertex. So this is clearly the case that, okay, maybe I should say, why were we thinking about these notions of transients? I mean, just to say, this is kind of a more natural thing to look at because it's a local notion. You want to say a graph that satisfies that locally, it's a transient graph. Maybe locally, it's a tree. So the walk will not spend any time near. This tends to be bigger at Y equals X, and a graph, a random walk on a graph that is locally tree-like will satisfy something like this, and that's maybe a more natural condition for you to expect decorrelation in the uncovered set or Gumbel fluctuations. So these strong transients imply weak transients, and it turns out our diameter condition. So this one, this diameter condition, global geometric condition, we can show implies strong transients. That's not obvious. Say 2, not 2. 2, sorry. Well, they're equivalent. So yes. So we can show this this global geometric condition implies this kind of local notion of transients in a strong sense. Maybe you could think these two things are equivalent. Right. So it turns out it's not the case. So we can. So there exists a graph which satisfies strong uniform transient, but not the diameter condition. 2. And these graphs are exactly obtained by taking products of things that are sort of transient in one direction, but recurrent in another. And so even though they are sort of transients in the sense that the walk will quickly get lost, which might lead you to believe that the uncovered set is decorrelated, still this graph does not satisfy the diameter condition, and therefore you will not have Gumbel fluctuations for the cover time. And there's kind of a third thing I've been alluding to it, but not really saying anything precise. So let's take S in R, and let's call TS okay, so this is a candidate for the cover time. This is a time that has a reasonable chance. It's a window where you might see the cover time. So U of TS, I remind you, is the uncovered set at this time. And let me define the product measure. So this is product over all vertices of the graph of Bernoulli law. This parameter e to the minus s. So I'm going to say that I'm going to ask myself whether the law of the uncovered set is close to this product Bernoulli distribution. So the third theorem is that these two conditions that I had here are equivalent to the third one. And this third one is exactly that the uncovered set is closed. So the total variation distance between the law of the uncovered set and this product distribution tends to zero. Yes?
I find it a bit confusing. Do I read correctly that this indicates that after a long time, the uncovered set is essentially a dust of single points?
Yes. So here we're looking close to the cover time. So you might expect a finite number. So typically you will, very important. You will expect here of order, basically a Poisson random variable with mean e to the minus s uncovered points.
So the uncovered site is just dust of points.
A dust of points, exactly. And we ask, are these points correlated or not?
I mean, before you get that far in time, probably they are more correlated. And I thought that is kind of a normalized picture of.
Yeah, so it's, I think, very interesting to ask whether if you look at a time which is not this, so this, might be here, there's a positive chance that the cover time has occurred. But if you look at something like, 75% of the expected cover time, you'll have many more uncovered points. And whether or not the structure of this is approximately IID in this sense, it's a very interesting thing. It's been partly studied, but even on the box, we don't have, even on an n by n by n box, we don't have full answers. So there's a very nice paper of Jason Miller and Per Lasouzi that studies this and suggests that there's a phase transition, maybe, as you increase the fraction of the cover time where you're looking at between things that might be, when we're very far from the cover time, then things are correlated, but not after some positive fraction.
Is the expected size of the uncovered set always decay exponentially, no matter what the geometry of the graph?
At the time here, at times. So the size, I think, as you increase S, you ask, is this? I think so. Yeah. I mean, yeah. But I think it will always have exponential tail. Yes. the cover, I would expect the cover time. So in 2-dimension, it's not expected to be a Gumbel random variable, but it's going to be, okay, maybe I should be careful. It's expected to be a random variable that's Gumbel plus a shift. And this shift, okay, it could be that this shift actually is not very well behaved. So I should be careful.
So it's not, I just thought it might be easy to compute expected cardinality. Maybe that's also already difficult.
Yeah, it's already non-trivial. That's right. Even on 2D, it's far from obvious. It was the content of this demo where it's presented to you. Good. So, questions on the results? Yeah.
Just about these uniform transience conditions.
Yeah.
You write max xy if y is taken to be x.
Yeah, actually,
Is it actually the same condition?
yes, because this is in continuous time. This is one of the advantage. The heat kernel is maximized on the diagonal.
Okay. And if instead of mixing time, I take the time to hit somebody, y, I don't know, z, the time to hit some z will it be the same?
Probably doesn't make a difference, but
Yeah.
yeah, it probably doesn't matter what you pick there. Yeah. So how much time do I have? Yeah, I have a bit of time to say something. So there's maybe two things that I would like to advertise in the proof of the result. Maybe I know that some of you in this room are familiar with at least some of these things. One is related to.
And sorry, just
yeah.
You say that 2 is not equivalent to CUT, but is it equivalent to WUT?
Oh no.
Because it is implied.
Yeah.
Okay. Right.
Yeah. No, it's actually I find it kind of surprising. I mean, this global geometry condition, it really is very simple, and it's kind of surprising that the answer has such a simple form. I think. I mean, if you take, maybe you can try to make a parallel with the problem of cutoff. And in cutoff, in the case of cutoff, I mean, this has been much more studied, but in some sense, not only we don't know graph general criteria that imply cutoff, certainly not general criteria that imply what the profile of the mixing is. It's not really expected that there would be something so simple. So we were very surprised when we got this. And, as I said, initially our belief was that the correct thing to look at was this condition. So two things that I want to mention. One is related to Gromov's theorem. So maybe, I mean, so I will be very brief, and I'm also a bit intimidated to speak about this when Terry is in the room. So, but if you have a group, G infinite group of polynomial growth, in the sense that the size of a ball of radius r grows like r to the alpha for some alpha that's positive. It probably could be some, you don't know what alpha might be, it might be 2.3. Well, it turns out that's not possible. And really, the graph in some metric sense, the group in some metric sense will look like just Euclidean sense. So I'm not stating this carefully. I think we would call this statement the Gromov-Hausdorff convergence, in the sense of Gromov-Hausdorff convergence. If I'm not mistaken, this topology was introduced for this statement, actually. And so why is this relevant here? So it's relevant because recently there was progress, I think a very nice paper of Romain Tessera and Matt Tointon, I don't know how to pronounce it actually. And so this will give quantitative forms. So let me not be very precise here. But in particular, they apply these results apply for finite groups, and basically vertex-transitive graphs are never far away from groups. And why is this relevant here? The reason is that if you look at this condition, maybe in the form that I've written it here, you will see that let's take, if we take R to be the diameter, so what I call D, then well, the volume of the ball of radius R, obviously that's n, that's the whole graph, and we assume that to be a bit bigger than R squared. Right? That's the assumption of this diameter condition. And so this Tessera and Tointon paper, one of the things that it tells you is that, well, because you're a bit bigger than R squared, because you're a bit bigger than the two-dimensional object, it has to be the case that the volume growth of ball, initially at least, is at least three-dimensional. So a bit like in a box, you know, in this flat box, you see that the volume growth is initially three-dimensional and then turns to two-dimensional when you reach the height of the box. And this paper actually tells you that, you know, that's going to be true in general, which is kind of amazing. So, so there exists some intermediate scale, let's call it rho, such that actually the ball of radius R must grow like at least R to the cube. Let's say at least R to the cube. So for up to radius rho.
So what is the condition under which this is stated? It's not two, but it's the opposite of that, or it's opposite inequality.
Yeah.
Here you are saying that D is too large.
Yeah, no, so I prefer to, this is why I prefer this formulation. It's the same thing. Yeah, so I put the N here. Wait, have I done this correctly?
Oh, I see.
Yes. Yes. Okay, I'm sometimes confused. Yes, I think that's correct. It's better to think of it this way. That's why I wrote it. So yeah, this is saying the you're a bit. I mean, it's natural. Yeah, it's saying you're a bit more than two-dimensional.
And the statement, last line of this word, I don't know if rho is not depending on n, it just seems a meaning.
Yeah, no, right. Rho is
rho
is some intermediate scale.
But you don't say how.
Yeah, it's you can say how, but okay, I don't remember on top of my head. And so, why is this relevant here? It's because I mean, this is, you know, a very strong statement. It really gives you a lot of margin when you want to. So analyze random walk on this group, because on this graphs, because that tells you that it's not too hard to see. So there's even really like an isoparametric inequality associated with this. It's not just the volume growth, but really you can check that the size of the boundary of a set in this region, you know, will be at least R to the 2, at least its diameter to the 2, as you would expect for a three-dimensional object. And because of this isoperimetric inequality, you can get control on the heat kernel of the walk. And you can show that PTXS must decay at least like t to the minus 3/2 or t less than the scale squared. So long as you're still in this ball, then the heat kernel must decay at least like the heat kernel of a three-dimensional walk. And yeah, so that's very useful because it's exactly the sort of thing that allows you to talk about strong transients and to prove decorrelation. So that's one thing I wanted to mention. There's a second thing that we do that I think is quite neat. And that's to do with that's to do with something called the Aldous approximation. So if I give you a set of size k in the graph, and I ask myself, what can we say about the heating time of these k points? The first time we'll visit any of these k points. And these k points, I don't tell you how they are. Maybe they're close, maybe they're far apart. I mean, I don't know. Yeah, so when they're far apart, you kind of expect that the heating time will be something like the minimum between k roughly independent exponential random variables. And so you might expect this to be itself exponential. So it turns out that there is a natural way to try and sort of quantify this, because associated to the set A, there will be something called a quasi-stationary distribution, where if you start alpha A, if you start from this distribution and then conditionally, and you run the random walk for time t, conditionally on not hitting A, this quasi-stationary distribution has a property that the law at this time is still the quasi-stationary distribution. And in consequence, if you look starting from this quasi-stationary distribution, the heating time of A will be exactly an exponential random variable. With some rate. And Aldous and Brown, they were, so this was a very nice paper in 92. They were able to compare the heating time of A starting from the uniform distribution or from some other distribution, it doesn't really matter. To the exponential distribution, and they obtain this kind of quantitative error bound. So this is the relaxation time, so 1 over the spectral gap, and this is the heating time.
This arbitrary vertex-transitive graph, is that the one?
Yeah, I think I think it's actually doesn't really require vertex transitivity. It's like it's quite general. It's really possibly bounded degree, but I'm not certain. It's not much more general than vertex transitivity. And if you look, I mean, this relaxation time, as soon as you're in sort of the polynomial growth regime that we're talking about, this will be d squared, and basically this heating time will be something like the volume. That's kind of always what it is. So you see that when you're at roughly at the diameter condition, then this is something like 1 over log n. So this is kind of heating time of sets are exactly what controls what you need in order to control the distribution of the cover time. And so a result like that is very useful.
The constants depend on K.
I don't think so, but I wouldn't swear.
Do you use this result for K, just K bounded, or do you need it?
Yeah, we need it for K bounded.
Okay.
So yeah, exactly. So the reason is that if you want to think of something like you might want to compute the expected kth moment of the uncovered set.
Okay.
Right, and then that's summing over all sets, and you want to control things like that. And so something like that is very important, very useful. When you're just above the diameter condition, you get something like that. When the diameter condition holds, you get a little low, and it turns out this approximation is kind of enough to deal with kind of the other direction of the theorem. So when you don't have the diameter condition, you want to prove that things do not have the Gumbel distribution. It turns out we need an improvement on this. And okay, so what we obtained, so again, all of this is with Jonathan Herman and Lucas Tessier. We obtained we obtained a better hair bound. And I think this is sharp. I don't think this can be improved. At least it seems like in 2 dimensions you cannot improve it. And so this improvement, which goes from basically 1 over log n to 1 over log n squared, might not look like much, but it's absolutely crucial in the proof of the converse direction. This is what allows us to handle cases that are close to the diameter condition, but this diameter condition does not. Okay, so I think I'll stop there. Thank you very much.
Any question?
So you explained about the diameter condition and these weak transients and strong transients. There was another thing that we saw in the ZZ case, that tau heat was of order n.
Yeah.
Is this tau heat being of order n equivalent to anything or similar to anything?
I mean, that's you would expect that in every sort of transient situation, basically.
So maybe it's implied by a SUT, but maybe it's equivalent to
that. Could well be the case. Yeah, I mean, you can sort of cut time of order n to intervals of size d squared, which is basically the mixing time. And you can ask yourself, in each of these intervals, did you hit x or not? And how would you check that? Well, the probability that you would hit it will be the expected local time there divided by the expected local time given that you visit it. And so that's why this sort of transience thing is natural, because if you do visit it, the transience tells you, well, the amount of time you spend there will be bounded.
Right. But is it equivalent?
So I don't know, but on top of my head, I would. Okay, I would say yes, but no, don't believe me.
Say yes, you say.
If you force me to say something, I would say yes, but yeah. Yeah.
Is it any simpler to think about sort of 2-scale version of it, where you take not quite infinite but huge plots, and within this you look at a large screen and you ask by what time would that screen be covered?
Yes.
But then you have kind of sequence of interlacements which come like thunderbolts, kind of traveling from infinity and disappearing each time, doing some damage and refreshing.
Okay, I like very, yeah, that's very true. So I mean, I don't know what is the status, but I think Jonathan and Luca and maybe Omer Angel, they're working on this problem that was raised in the work of Jason and Perla on the transition between correlated to decorrelated when you're far away from the cover time. And I think they will have a proof of this at some point, of this transition, and it's exactly this sort of idea that come into play. And like, so you need to look at, the key question is really sort of on mesoscopic boxes. So somehow this improvement kind of allows you also to say something interesting about how you cover mesoscopic regions far away from the cover time, if that makes sense. Something like that. I hope, I think what you're saying is exactly the philosophy that they are using to approach this problem.
Any suggestions what happens when the diameter condition fails? Maybe at the condition, so when it's exactly log n, like instead of Gumbel, any ideas?
This I wouldn't venture. I think in 2D, there's a, even in 2D, this is open. Yeah? So in 2D,
there's Biskup and Loidor related to these things.
Yeah, but I mean, they really don't do the 2-dimensional case. But yes, I mean, so it's believed to be a Gumbel random variable that's shifted. The shift is related to the kind of living quantum gravity measure associated close to the cover time. So in brief, the walk has walked so much that when you couple its local time with that of the Gaussian free field, the coupling is very strong, and you'd expect the living quantum gravity measure, the critical living quantum gravity measure, to be related. But I can't remember if the shift is the log of the total mass or the total mass. If it's total mass, then that's kind of bad news because it has bad moments. But log is good. And at the critical sort of diameter thing, I mean, there will be a shift of some sort, but what is it?
Maybe specifically in your example of the theorem that satisfies SUT, but not 2. Maybe that specific example is easy, relatively.
Possibly, but we were not really able to get a convergence in distribution. Like all sorts of things start to go wrong. We tried actually, we didn't succeed. Yeah.
Any other questions?
A very trivial remark. You mentioned you don't have a name for a graph that goes up to infinity, but you want to treat it as a single object.
Yes.
So in the language non-standard analysis, you call it a non-standard graph, non-standard finite graph.
Non-standard finite graph. Okay.
It's just a linguistic change. It doesn't actually do anything for you.
Yeah. Still, it's useful to have a name for it. I always find it a bit awkward, this way of talking about things. So
yeah, that's for non-standard analysis. That's the whole somehow the framework.
Okay. Thank you.
Is there a language in which non-standard language to write a proof?
You can. I mean, it's you call it all. You call it infinitesimal. I mean, it's a very similar dialect of mathematics. Yeah.
Okay, so maybe we can have a 5 minutes break and then we start the second part. Thank you very much.